going to continue talking about this, and it's actually going to make more sense. And I probably already said that the highest number in your exponent, if you had a function, the highest exponent tells you how many roots you have, how many solutions you have. They may or may not cross the x-axis if they're not real. We're only going to work with real roots. So we're going to say that this guy has 3 roots. And we have another little thing to say. We're going to take the exponent minus 1. We're going to do exponent minus 1. This tells us how many terms. You might want to add this to your sheet. Then we're going to take the terms minus 1. And this tells us how many inflection points we get. So we can tell a lot about your function just by looking at what the highest exponent is. We can also say how the ends behave based on the highest exponent. So if we have an even number, if n is even, such as we know that a is positive, my ends or parabolas will go up. Even if I did x to the 4th, my ends will still go up if a is positive. So we describe your end behaviors as up on the left, up on the right. They're both going up. Any even highest exponent will behave the same. If it's a negative, if there's a negative in front of this, then they will both turn down. So if I did this, both of them on the end would turn down. If I did this, they would both go down. So they behave the same when my exponent is even. When my exponent is odd, we have a little bit of a different story. When my exponent is odd, such as this, the left, when a is positive, this means it's positive, the left will go down, the right will go up. Okay? If a is negative, which means I have this, then, oops, where is it? Then here, then the left will go up, the right will go down. It will just go the opposite direction. Kind of makes sense. If when you do an even one and it's positive, they both go up. It's negative, they both go down. On an odd, one's down on the left, up on the right. When it's positive, they have to switch when it's negative. Anybody have Mr. Baker in here? Doesn't Mr. Baker do a thing, Saturday Night Fever thing? John Travolta. He still does it. So that's your end behaviors. So this is how we talk about your end behaviors, and it's going to help us. If we find the roots of your equation, and we know where your ends go, and we know how it behaves, what it's supposed to do, how many turns it's supposed to take, we could sketch it without using your calculator. So that's our goal, to describe as much of these functions as we possibly can without picking up your calculator. We're going to pick up your calculator for when we need to do mins and maxes. Okay, so these are just like things that we're going to look for. Now, we also like to find all the zeros of your function. The roots are on the x-axis. Therefore, we're going to set y equal to 0. And we always find your y-intercept, don't we? We always find your y-intercept by setting x equal to 0. And usually I tell you block out your x's, right? So that this way your sketch is on target. That helps your sketch. So if you blocked out all these x's, what would y be equal to? 0. So it's the same as if I plugged it all in. So we kind of block out all our x's, so y would be equal to 0. That helps us. Now, How many roots should this guy have? 4. It should cross the x-axis 4 times. If we have real roots, we should have 4 roots. How many turns? -1. 3 turns. How many inflection points? 2 inflections. Now, I know you don't know what inflections are, but we're about to figure them out. Now, let's find where your zeros are. How should your ends behave?
Both going up.
They both should go up. Good. Both sides up. It's even, and A is positive, greater than 0. So at the end, my things both should go up. So I set my y equal to 0, and I find where does this thing cross the x-axis. So what can I factor out of here? X squared. I've got everybody has at least an x squared. And what's left? Take out an x squared. X squared. Okay. So now let's factor this again. Stay with me. You're going to see it makes so much sense. We described most of it already. So now, x minus something, x plus something. Give me 2 factors of 20 that the difference gives you 1.
X minus 5 and x plus 4.
Good. We set these guys equal to 0. Now, see this x squared? When you take the square root of something, don't you get a plus or minus? But on a 0, we really don't. But we call this a double root. This is taking care of 2 of my roots. They're both 0. And we're going to see what a double root, how a double root behaves. This guy is set equal to 0. I'm a 5. This guy is set equal to 0. I'm a -4. Now, a double root does not pass through your x-axis. It bounces off your x-axis. So if I'm trying to sketch this guy, I know that when x is 5, here's a root. When x is -4, here's a root. When x is 0, I have to bounce off that. I can't go through it. That's my double root. Now, Monisha just told us where my ends go. My ends go up, right? So, up, up. This has to come through. What do you think this is going to make? A W. Good. I somehow got to get back to that little spot, right? So I got a curve to get over here. I bounce off the axis, and I curve again. Now, what we don't know is how far these go. I would kind of, as you do more of these, you'll kind of sense when it's symmetrical. But could these be symmetrical?
No.
Why not?
Because one is 4 away from 0 and the other one is 5 away from 0.
Very good. So one is 4 away, one is 5 away, which probably means that one little loop is a little bit longer than the other. But I kind of have the sketch. I have 1, 2, 3, 4 roots. I also passed through the 0, 0. I knew my end behavior went up. And I know my double root doesn't go through my axis, it bounces off. That's pretty good to see that equation and to know that we can sketch that. Otherwise, we have no place to start but put it in our calculator. Now, when you put it in your calculator, one of these actually does come a little bit longer. So let's have you put this in your calculator and see what else we could tell about this.
Wait, what are we putting in our calculator?
This original guy. That's x to the 4th, the one I just wrote all over. I'm going to call this A, B, and C.
Do we have to do the window?
You might, I think that goes pretty far down. You might just have to lower your Y. Just change your Y min. Or your Y min has to go pretty far down. Just go back to a zoom 6 and then change your Y min. You'll hit the X's, but you probably won't hit the Y. You won't hit the loop. I'm not sure where it goes down to, like 120 something. Come on, you know how to change your windows. And what would we call C? An absolute what?
I mean, not min.
Min. Okay, we've got a relative min, an absolute min, and an absolute and a relative max. So let's find what those are. Remember, we go 3 decimal places. I noticed a lot of you on your test didn't go 3 decimal places. I didn't take anything off, but you need to start going 3 decimal places. And it's easier sometimes to label the letter here and then find the point here. Okay, so we should have our relative maxes and mins. Now, let's talk about this inflection point right now. Well, let's not talk yet about it. I'll do inflection on the next one. Can everybody find the rest of this that we did? We can do increasing, decreasing from this also. Which do we use, the Y or the X when we do increasing, decreasing? Well, we look for the Y to be increasing, decreasing, and we state it in terms of what interval do we give it, the X intervals. Okay? All right, so let's try another one. I want you to just be able to realize we're doing the same exact thing, we're just adding a little bit more. All right, so let's talk about this guy. How many zeros should this have? 3 zeros. How many turns?
2.
And I'm going to add the 1 inflection point. This time we'll do an inflection point. Okay, what does my end behaviors look like?
Left goes down, right goes up.
Good. Left down, right up. It is odd and it is positive. So the left is going down, the right is going up. Okay? Where's my y-intercept? I got both x's. If I take them out, what is y equal to? Good. No, I'm going to take this x out. The x's are going to come out. So what is y equal to? 0. So I know my y-intercept, that helps me. So I need to find my roots to see where this is going. So I'm going to set my y equal to 0. This is going to find my x-intercept. Where are my zeros? My roots. So what can I factor out of here? X squared. What's left?
X minus 3 halves.
Okay, so I'm going to set these both to 0. Well, what do I notice here? What is it when I have an x squared equals 0? This is a double root. That means it's going to bounce off the x-axis and not go through it. And then this one I'm going to set to 0. This is 3 halves. So I should be able to get some kind of sketch here. I know at 0, I bounce off, and at 3 halves is my last one. Now, the ends go down on the left, up on the right. At the 0, I can't pass through. I have to bounce off, so it's got to go like this. See it? This guy's got to come through. So somewhere, I'm making a loop. We were able to graph that without your calculator. Now try it on your calculator. Does this mean that this loop is going to be that small? That I don't know. But I know that that's going to be the general look of my graph. And remember, we're sketching. We're sketching. So let's put that in your calculator and see. You might want to just do a zoom 6 to get back to normal. I think the zoom 6 would do it for you. So somewhere that's pretty close to that axis, isn't it? It's pretty close to my axis. Yes? If you need to go a little bit, see a little bit more exact, set your y, your min and your max, like from -2 to +2. And it'll kind of zoom in with your y. I don't want you to use a zoom. I want you to use your window. So set your y max from -2 to +2. Do you kind of see it a little bit more? Can you see it pass over? It's probably a little less than the 1/2 on the y. But you can see the little loop in it. So I know that A is called what? A relative max. And what do I know that to be already? 0, 0. And B is called what? A relative min. Okay. What's my domain? All real numbers. What's my range? All real numbers. Where am I increasing? My y is increasing, coming up like this until I hit what? 0. Give me the x interval. And then what am I doing from A to B? Decreasing. From 0 to what B point? Oh, did we figure this out yet? We didn't figure out your B. What's your relative min point? Anybody get a relative min?
Relative min was 1 and -1/2.
Okay, so give me to my x to 1, and then where am I increasing? From 1 to infinity. Okay, now we said 3 roots. We've got 3 because we have a double. 2 terms. 1, 2. We have 2 terms. 1 inflection point. Now I want you to watch here for a second. Let's talk about what an inflection point is. Before we can talk inflection point, we have to talk concavity. What does a cave look like? If you saw a cave in the woods, what would it look like? A cave. What would it, like, draw me a little symbol with your hands. It would look like this, right? I would see this little opening like this. I would see a cave that goes like this. We say this is concave, cave down. Concave up means we just took the cave and we flipped it over. Concave up. And this guy is concave down. I kind of drew it on your papers for you. Okay, concave up, concave down. Now, watch up here for a second. We're looking for caves. I see a cave right here. He concave down. Okay, now I see a cave right here. He concaved up. Somehow, they shared the same interval in my function. They shared this piece from A to B. So I do this and I say, this is my inflection point. I'm going to call this C. C is an inflection point. That means halfway through, I decided to switch. I was concaving down, But then I said, whoops, I'm going to concave up. So because it's halfway, you're going to find your average of your x's from your min to your max. We're going to take your min plus your max x divided by 2. So this guy was at 0, 0. This guy was at 1, negative 1/2. So we're going to add 0 plus 1 and divide it in half. So this gives me 1/2 something. Now, sometimes, most of the time, we can take the average of the y's, but not all the time, depending on where we fall. So we're going to go to your calculator, and we're going to let the calculator tell me what the value of y is. We're going to go second calc, number 1, value. And we're going to say, when x is 1/2, tell me what is y. And your calculator is going to tell me what is y. So what does it say?
You add the min and max x's.
Yep.
And then divide by 2 and then find the y value.
Yep. So it should say 1/4, right? So my inflection point is 1/2, 1/4. Sorry, negative 1/4. So we found your inflection. So now I can say concave down. I'm concaving down from negative infinity up right at that inflection point. That's my 1/2. Use the x value. Then I'm going to concave up from 1/2 to infinity. Look that over for 1 second, guys. Somebody's outside that.